Okay, we're going to look at a problem from section 4.6. Actually covers a lot of chapter 4. We have a 7th degree polynomial, and we have these 9 different items, instructions that we're asked to do with this polynomial. So the first is to list all possible rational roots. So we're looking at the leading coefficient, which is 1. We call that A, and its integer factors are plus or minus 1. The constant term is 12. Its integer factors are 1, 2, 3, 4, 6, and 12. And so when we divide all of the integer factors of B by the integer factors of A, in essence here, and this is part A, we get all of our possible rational roots. Okay. Now the next part, I'll check that off. We're making a chart of all possible positive real, negative real, and imaginary. It should be an S for roots. So we're using Descartes' rule of signs. So we'll make a chart here, and this is part B. So we have positive, negative in our complex. And so in order to determine the number of positive possible roots, we're going to look for P of X, and we're going to look at the number of sign changes. So we go positive, positive, next term is negative, then negative, positive, negative, negative, positive. So how many sign changes do we have? We have 1, 2, 3, 4. So that means for positive, we could have 4, or we could go 2 less 2, or 2 less 0. And then we would substitute negative x. So if we do negative x to the 7th, that'll be a negative. Negative x to the 6th, that's a positive. Negative x to the 5th is negative, but you're multiplying that times another negative, so that's positive. Negative x to the 4th is positive times a negative. Negative x to the 3rd is negative. Negative x squared is positive, but there's a negative. Negative x times negative is positive, and then the constant term is positive. So we have 1, 2, we have 3 sign changes, so we can have 3, or in any even less 1. Okay, so we look at positive, so we could have 4, and if we have 4, since we have to have 7 roots, we could have 3 negatives, and that would give us then 0 complex, because there's our 7 roots. Another possibility is 4 positive, 1 negative, because we can go down by 2. There would be 5. That would leave us with 2 complex. There's no other combination with 4, because the negatives have to either be 3 or 1, and combination or complex has to be an even number. So the next choice is 2. And if we have 2, the negatives at most we can have is 3. We learned that from here, so that's 5. So there's 2 more roots. There we go. They'd be complex. Or we could have 2 and 1. There's 3. And we could have 4 complex roots. And then we could have 0 positive. That's a possibility. And if we have 0 positive, again, we could have 3. That would leave us with 4 in the complex. Or we could have 0 positive, 1 negative, and that would leave us with 6. So there's all of our combinations of positive, negative, and complex roots. And in the end, we'll figure out which one it is, and we'll come back to that. Okay, now it wants us to identify the roots and then factor. So there's a lot of possibilities here if we were going to start plugging these numbers in and doing synthetic division. So here's really a time where we want to use our graphing calculators. And so I've already put it into my y equals. And my window, I'm just doing negative 10 to 10 for both the x and the y, mins and maxes. And here's my graph. So right now it looks like a triple root there. It looks like maybe a triple root there, maybe a single root. And if that's the case, we have that possibility, right? 4 positives, it looks like maybe a triple and a single, and 3 negatives. but it's really hard to tell. We're kind of wide with our window, so I'm going to narrow the window down, and I'm going to look in here. So what I'm going to do to try to, I'm just going to go from 0 to 4. And my y mins, I'm going to make that a little bit smaller. I'm going to go -4 to 4. So I'm just kind of zeroing in or narrowing in on that portion of the graph. Well, sure enough, it looks like I have a triple root at 1. To confirm that, I'm going to go second calc 0. Let's see, I am at x equals 2, so I'm going to use my left arrow. Here comes the cursor. I'm going to get to the left, so I'm to the left of that and hit enter. I'm going to go to the right of that, hit enter again. And let's see, sure enough, 1 is a root. Okay, so now I'm going to start doing some synthetic division, and let's see where that takes us. Okay, so again, I'll rewrite that my function here, f of x, is x to the 7th plus x to the 6th minus 8x to the 5th. I'm just going to finish up here. Oh, that should have been a 23. X to the 3rd minus x squared minus 24x plus 12. Okay, so again, it looks like 1 is a triple root based on that kind of that S curve there. So what I'm going to do is I'm going to do synthetic division, and I'm going to try it 3 times and see what happens. So 1, 1, that's 2, 2, -6, -6, -10, -13. Oh, that should have been +13. Going a little too quick there. So that gets us to 12, 12, -12, -12, 0. Sure enough. So let's try it again. If 1 is a triple root, then we should be able to do this 2 more times with our synthetic division. There's 3, -3, -3, -13, 0. Okay, so it's at least a double. And because I see it goes through, right, we know it can't be a double because a double would have bounced off. So let's see, 4, 1, -12. Sure enough, that is a triple root. Okay, so in terms of identifying roots, I'm going to come back over here to part D, and x equals 1 is a triple. Okay, we know we have 4 more roots. So now I know that I saw that my roots were on the other side. So let's just go back. Let's start from the beginning. Again, going back to our -10 to 10. And here's our graph. So let's see what's going on over here with our roots, because the other one I saw over here didn't look like it was going to be rational. It was in between 1 and 2. So maybe it's 1.5, but it didn't look like it. So I'm going to zero in over here, close in it a little bit. So my window, I'm going to change that from -4 to 0. And I'm going to just go from -2 to 2 and my y's and see what I see here. So here, oh, so actually look, it looks like right now we have a double and a single, which makes sense, right? Because we already had 3 positive. We knew there was 1 more positive, that would be 4. And if we look over here, we could have 4 positive, 3 negative. So it looks like what we have here. And it looks like -2 is a root. It looks like it bounces off there. So I'm going to go second calc value this time. Plug in -2. Look, there we go. We get 0. So we know -2 is a root. So I'm going to confirm that over here with my synthetic division. So I'm going to do -2. So 1, -2, 2, -4, -3, 6, -6, 12, 0. Now, at this point, I actually feel like I can factor this. I see my pattern, but because I suspect -2 is another root, I'm just going to do negative 2 again. So 1, negative 2, 0. Negative 2, oh, no, that should have been 0, right? Negative 2 times 0, so negative 3, 6, 0. Okay, so here I am. I'm looking, I've got this function f of x. I have 1 as a triple root, so that's x minus 1 cubed. I have negative 2 as a double root. And look at what's left. I have x squared minus 3. Okay, so double root, triple root. If I take x squared minus 3, set it equal to 0, right? Absolute value. And look, I get, oops, 2 more single roots. Okay, so I'm coming back to here. X equals negative 2 is a double. X equals negative root 3 is a single. And x equals positive root 3 is a single. So triple, so there's 3, 4, 5, 6, 7. So that matches our degree. We have 3, 4 positive, 2, 3 negative. There we go. So that matches from our Descartes rule of signs. Let's see. So we've factored it. Actually, and it wants us to write it as n linear factors. So just to go back here, what I will do is there's our x minus 1 3 times, our x plus 2 twice, x minus root 3, x plus root 3. So there is our n, our 7 linear factors. Okay, let's see, what else does it want us to do? We've identified our roots, we've made our chart. Let's find the y-intercept. It's the constant term. So our y-intercept is the coordinate 0, 12. N behavior. Okay, we have an odd degree with a positive leading coefficient. So the limit as x approaches negative infinity of f of x will be negative infinity. And the limit as x approaches positive infinity of f of x will be positive infinity. So we've got our n behavior. Sketching a graph and identifying, so this is one of our new topics now, local minimums and maximums. Okay, so let's go back, let's zoom out a little bit, and let's change our window. And I noticed when I was at 10 that I didn't see the top of my graph, so I'm going to make that to 20, and I'm just going to change my scaling to go by 2s. And let's see what happens. Whoa, we're even higher than that 20. So let's see, make it 30 and see. Okay, so here I know I have the double root, and again, because we've expanded our window, we're not seeing it, but we know we have a double down and a single. We come up here down through our y-intercept, triple, single, and back up again. Okay, so looking at where my roots are in terms of scaling and my y-intercept, I'm going to go by 2s. And here I'm going to go each one by 1/2, so that's negative 1. That's negative 2, negative 3, 1, 2, 3. Okay, so let's see. I have, again, a triple root at 1, a double root at negative 2, and now at root 3, so coming back, I'm going to go back to our home screen, right? Square root of 3 is about 1.7. So I know that I have somewhere in here a root and somewhere in here a root. So sketching my graph, we're going to come up, a double down, come back up through a single. I saw my graph went up, comes down through 12, triple root, and back up again, and there's and it fits my n behavior. Okay. So we've done everything we've asked except for now the last thing is identifying what we're calling local minimums and maximums. Again, that's one of our new topics. And basically what we're saying is that in an area, in a small area, there is a local, so local to that, maximum value. So I see it's generally going to be what we call our turning points. I'll write that up here. So our turning points are our local min and max, and we're specifically talking about the y values, although we'll identify the x and y. So I have one here, one here, one here, and one here. So right, that's going to be a local max, minimum, max, min. Well, the first one I knew was a double root, so my local minimums, the first one is going to be at -2, 0. Oh, I'm sorry, that's a maximum. What am I talking about there? Right, we're at max because we're turning and going down. My other max is going to be here. So to find that, I'm going to go back to my calculator, back to my graph. Here it is, and I'm going to shorten my window a little bit again. So my window, I'm going to go from 0 to -4 rather to 0. Okay, and this is the local max. This is right here on our graph. That's this point here. So we'll go second calc maximum. There's my cursor. We're going to move it so that we are to the left. It's close enough. Now I'm going to move it to the right. It's asking for a right bound. I'm going to use that as my guess. And there is the local max. So they give you the x value and the y value. Going to 3 decimal places, -0.597 and then 21.194. Okay, here and here will be our local min. So when I go back to my graph, I can't really see that very well. So again, I'm going to change my window. My y values here are too big. So I'm going to go from -2 to 2. And you'll see now that we've taken a smaller view. See, there's our relative min. So to find that second calc minimum, okay, I'm to the left. Now I'm going to go to the right, hit guess. And so there's my minimum. It's at -1.828, and the minimum value is the y, -0.228, and you can round or truncate. And then remember, I had another one right over here. So to find that, I'm going to change my window to go from 0 to 4. I want to go on the other side of the y-axis. So here we are down here. Second calc minimum. So we got to, let's see, we've got to move our cursor. So here we come. Okay, I'm to the left. I hit enter. To the right, I hit enter. Give it a guess. And there we are. The other min will be at 1.569, -1.263. So there's our two local minimums. Again, one here, our two local max, one there, one there. Those are our turning points. And our graphing calculator is really the only way to find that until you get to calculus. So lots going on in that problem. Hope this helps, and we'll see you soon.